Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Susan Mullally with us today. Hello, Susan.
Hi, Frank. Thanks for welcoming me here.
Well, thank you for agreeing to talk about your very awesome article, which we'll get to very shortly. Susan, where are you located at?
I am in Baltimore, Maryland. I work at the Space Telescope Science Institute.
Ooh, very cool. Very cool. And it is March 8th 2024 as we record this. And is Baltimore in its spring, or do we still have a little snow on the ground?
We've just started spring. The daffodils are in bloom. So
Awesome.
yellow in my front garden. It's great.
Pretty, very cool. So we're definitely having spring here in Phoenix. I'm in Phoenix, and we do have grapevines. We have about 5 grapevines, and the first ones just threw out their very first new leaves for the year. So I'm very excited. I know, it was very cool. We got a lot of grapes last year, so I'm looking forward to this year.
You make wine out of your grapes?
Not yet, not yet. Any wine I made, you probably wouldn't want to taste, but they're doing great. It's awesome. And Susan, what do you like to do for research?
I am an exoplanet scientist. I like to especially work in time domain for exoplanets. I actually came from lots of experience looking for transits in the Kepler mission and the TESS mission, which is currently going on. So that's kind of where my background came from. So I like to find the planets. I like to determine which ones are there and how can we actually go about detecting them.
Well, I think
the article we're going to talk about here today is actually kind of a bit of a shift from my usual way of doing science. Because the other thing I was interested in back in my days as a graduate student were pulsating white dwarf stars. Nice. So, that end stage of low mass stars, right? And I was worried about what kind of pulsations, what kind of variability we could find on those stars. Right. So the paper we're about to talk about is actually kind of cool because it brings together my 2 pieces of research, which are these dead stars and my interest in exoplanets.
Very nice. Very cool. Was that a serendipitous discovery? Did it just pop out?
You mean working on planets around white dwarfs?
No, on the imaging we're going to talk about here. Was that a serendipitous?
Serendipitous? Oh, no. We planned those observations.
Okay.
We asked the TAC to give us time to look for the planets that we have now maybe found.
Very cool. Very cool. And that is going to bring us to this super awesome APJ letter. It is open access. It's the open access era, people. Go grab a copy for free. JWST directly images giant planet candidates around 2 metal-polluted white dwarf stars. And Susan, take us away.
All right, thanks, Frank. So yeah, the title sums it up pretty nicely. We found 2 planet candidates around 2 different white dwarf stars using JWST. The team that did this work is listed there. A lot of the initial analysis was done by those early co-authors you see there, John Debus, Misty Crackraft, the graduate student Sabrina Paulson at Oklahoma, and Fergal Mullally, who is now an amateur astronomer, actually, who works for the energy company here in Baltimore.
Yeah, very cool.
So we as this team, we pulled together people who've been working on exoplanets and on white dwarf stars. So this brings together people from Oklahoma, as well as Boston University with J.J. Hermes, people at the Goddard Space Flight Center with Tom Barkley and Elisa Quintana, and Bill Reach, who was a Sophia scientist.
What a great team. Good.
So it's a diverse team. We were across all time zones in America. We pulled it all together to do this research, which has been super fun.
Nice.
Yeah. So let's see. Let's start by just kind of giving you some context as to why we decided to go look around white dwarf stars for planets. Okay. Kind of the big question that we've been trying to answer is what happens to the planets after the stars die, right? Like, we know that almost all stars die as white dwarf stars, like at least all low mass stars. Yes. But what happens to their planets? Now, the kind of the canon says the inner planets should be eaten up and destroyed or tidally disrupted and thrown away, but the outer planets should just sort of expand outward and should still be there,
Okay.
right?
Yep.
So we said, well, if they should still be there, we should be able to find them. And so that's why we went looking. Now, this is not a new field by any means. People have proposed that there are planets around white dwarfs since we've started finding planets and started thinking about what happened to them.
Yeah.
And there actually has been lots of indirect evidence that says that these planets might exist. And one of the key pieces, the first pieces of indirect evidence that we have been find that there are planets around these white dwarf stars is the evidence of metal pollution in the atmosphere of white dwarf stars.
Okay.
So white dwarfs are typically just a layer of hydrogen, some helium underneath. So, and all you see then in the spectrum is hydrogen lines, your wonderful Balmer series. This is what I studied as a graduate student. So I loved these spectra. They were so clean with these beautiful Balmer series running through the data, and that was it. But then some of them have just a little bit of calcium, a little bit of magnesium, a few other elements. And the question is, why are they there? Because you have white dwarfs are these super dense stars, right? And so if you put something heavy on the surface of that star, it should sink out of the atmosphere, right?
Yes.
So why is it there? It's that any material you put there will sink out on timescales of potentially like a year.
Right.
Like really short.
That's the important part is they disappear quickly.
Yeah, really quickly. Some, depending on the temperature of the atmosphere, could be as like 2 weeks, right? Like super fast. And so the question is what got them there. And so people have pondered all sorts of ideas, and the favored theory is that there's a widely separated planet, giant planet, that is throwing in remnant planetesimals, asteroids, comets, whatever, in towards the white dwarf, at which point they get disintegrated into kind of a cloud of gas and dust, and then they fall onto the atmosphere of the star. So you actively have material constantly falling onto the surface of the white dwarf. And that material had to be thrown down there reasonably recently, right? And we expect it to come from there being a widely separated giant planet.
Cool. Okay.
So that's the indirect evidence. We also see some evolved stars that have known exoplanets, for instance, as well. So we know that they at least survive that far around like red giant stars.
Right.
So there's these little pieces of indirect evidence that they should survive. Right?
Yep.
Okay. So we said, well, JWST is pretty cool. I bet you we could detect these planets.
Yes.
And so we said, well, what would we want to do to find these planets? Well, we would first pick ones that have this metal pollution, because that's already an indication that there's likely a planet there. But then we said also, well, what's going to improve our odds of seeing a planet if it's there? And that is, well, the star should be somewhat young, meaning that the planet would still have enough heat that it would glow more brightly.
Cool.
And we'd want the whole system to not be too far away, because again, it gets dimmer.
We want to see it.
Yeah, exactly. So we needed to look around nearby white dwarfs that are not too old and have metal pollution. And that's what defined our sample of stars. And, yes. And while we could have observed way more, we decided to go with 4 because that was the minimal case that would give us an interesting sample, given how common we think planets are around A and F type stars.
Okay.
So if we didn't find any, it essentially at a 1 to 2 sigma level rules out planets around these kind of stars at greater than 1 Jupiter mass.
Yes.
Something like that, if you believe our current demographics of that, but you know.
Good. Okay.
It was a reasonably strong, given what we already knew, it was a pretty strong limit. So we went after these 4 white dwarfs. I'm just showing 2 of them here because we only found evidence, or really obvious evidence, for planets around 2 of them.
Okay.
And that is WD 1202 and WD 2105 here. Yeah. And so this just tells you a little bit about the white dwarfs themselves, just to kind of ground ourselves as to what stars we're looking at. They're about 10 or 15 parsecs away. based on their effective temperature and their log G, we can get a mass for the white dwarf. And so the first one is 0.6, which is very typical for white dwarfs. And the other
Yes.
one's a little bit more massive at 0.7 solar masses.
Oh.
Using that information, we can then infer what its main sequence mass is. And so these are heavier than the sun. One's at 1.3 solar masses and the other was at 2.5 solar masses. So that WD-2105, I think that makes it a star in its main sequence stage. I'm
Yeah.
a little foggy on the limits there.
That's okay.
Yep. And then we also can then infer what, using our stellar models, we can infer the total age of the system. So that includes the age as a main sequence star, and then the cooling age after it became a white dwarf. So you're looking at a 5 gigayears, so something very similar to the age of our own solar system for WD-1202, and something that is 1.6 gigayears for WD-2105.
They're fairly cool at about 10K.
Yes, that's the temperature of the white dwarfs. So they're actually both very similar in temperature right now.
Yeah. Okay, cool. I'm with you.
Okay, awesome. So those are the two stars. Why don't you at this point go down? This reports, the paper now is reporting what kind of imaging we got. So we got MIRI imaging of these.
Take a look.
Of these, yes, exactly. So here's a zoomed in piece of the image of the white dwarfs. On the top, you have WD-2102-232.
Yes.
And then on the bottom, you have WD-2105-82. So that first image is really our reduced calibrated image of the white dwarf, zoomed into like 70 by 70 pixels or so, 65 by 65 pixels. Look, it's right there in the caption.
Right.
Right.
Yep.
So you're not looking at very much of the sky. Each pixel is 0.1 arc seconds. So there's a scale on there just to kind of see. So you can see that the central star there with the kind of hexagonal shape around it. That's very typical for a JWST image. That's what the point spread function looks like.
Yes.
You remove the star, so you fit what you expect the star to look like for a point source. You're left behind with this little smudge right next to the star, and that's our planet. And you can do the same thing in the lower one, though that one you can see very cleanly without removing.
Cleaner, yeah.
If you then do the same thing, model it as a point source and try to remove away the planet,
yes,
and you cleanly remove the planet. So that's why the last image is there, is to show you that it is indeed a point source. If we remove, if you fit and remove a PSF, you actually cleanly remove that smudge that we are calling the planet.
Cool.
Yeah. So this is what the images look like. And so this is our evidence for this. We have more than just one filter. So what you're looking at here, we actually took images of these white dwarfs in 4 different filters. This one that you're looking at here is at 15 microns.
Okay.
We also took it at 5, 7, and 21.
Great.
So we have 4 bands. And so in addition to seeing a cute little smudge next to the star, we actually have colors for these smudges. So if you actually go down to figure 2, I believe it is.
Sure.
I mean, we can look at the tables of numbers if people love tables of numbers, but I think
figures are great.
Nicer. So this is what you're looking at. The black line is what you want to draw your mind to right away. Is those are the 4, the brightness we measured for the smudge, the planet, for all 4 filters compared to models of giant planets by one is by Burroughs and the other is Beck's.
Yes, Burroughs who just came on, and then
yes, thank you.
Okay.
There are other models we can compare to. These are the 2 we had at hand at the time.
Sure.
And so what you can see about the black line is that indeed out at 15 and 21, you see that it's getting redder. It's increasing flux. Is just what you expect compared to many low mass, Jupiter mass type planets. The unusual thing about our colors is that they're a little too bright in 5 and 7 microns. You might actually expect them to be much dimmer at 2 or 5 masses. depending, but how much do you trust our models and our understanding of all the different ways that a distant exoplanet might look? So they seemed very red, and so they don't match perfectly to the models, right? We would love it if they just, like that line you're pointing at, if it matched the purple line, I would have been so happy. But it never perfectly matches the model that we have, right?
Okay.
But that is our other piece of evidence, is that both those smudges are quite red. They show an increase in flux, especially out at 15 and 21 microns compared to what they are at 5 and 7. We also don't see those smudges in, previous Hubble or Spitzer observations, for instance.
Okay.
So those, but then again, they're so close to the star. I think only WD 2105 we probably have seen separation, especially in Spitzer.
Definitely.
Yeah, part of the problem with Spitzer is this is the thing, like Spitzer was too small to do this. Like it didn't have the aperture to get the amount of flux that you needed, right? AST has the resolution, but it's not at the right wavelengths in order to really get lots of flux from the white dwarf. I mean, one of the things I skipped over is why it was so advantageous to do JWST around white dwarfs.
Okay.
So great is that for imaging, white dwarf stars are already, it's like they're their own coronagraph. They're so dim, they don't put off that much light, especially out in the infrared. So the contrast between a planet and the white dwarf star out at 15 microns is only like 1 in 100.
Nice.
Right? So you don't have to worry about this big glaring star washing away your planet.
Yeah. Very cool. Good.
You don't have to first block it out like we do with coronagraphs for a lot of these young stars. People are looking for planets around.
Very nice.
So that was one of the cool ideas for doing imaging. I mean, we weren't the first to do this. Actually, John Debus, who's on this team, tried to do this with Hubble for about, I don't know, half dozen stars as well. But he could only get mass limits of about 5 or 7 Jupiter masses. So he was not as sensitive to really low mass planets.
Right.
With Hubble.
Okay.
Because of the wavelength range.
Very cool.
Yeah, so it's nice to have 6 meters of glass in space at, at 15 microns. I have to say, I'm quite enjoying it.
We'll come back to that. We'll come back to that. Okay.
Yeah. So I guess the other thing that's really cool about it, so we found really good, convincing evidence that these are planets. Now, as good scientists, we then said, okay, well, what could be fooling us, right? What else could have this sort of features, right?
Yes.
And so this is where I want you to bring up that other image that we talked about.
Okay, let's go ahead. We're going to do a little stop share. I'm going to bring up something new, and this one. So while we were looking at that zoomed in piece of our one little star, this is actually the entire MIRI image, and it kind of gives you a perspective of what I'm talking about. So yeah, you're circling the white dwarf there, and you can see the little planet smudge up and to the right. But if you look across the entire image, you realize you're not just looking on blank sky, right? There's all sorts of other things in this image. There's a star right next to it, but that we knew was a star. That's been found, and we have colors across other places. But there's all sorts of non-resolved things in this image as well. You can see smudges, anything that doesn't have that nice little, hexagonal or snowflake thing to it is essentially a smudge. And is probably a galaxy. So for some reason, the universe decided to put our galaxy amongst a whole bunch of other galaxies and make it hard for me to find planets. And so you're not just, unfortunately, some of those galaxies are even brighter than our planets. And so they are the predominant thing we're worried about being confused by. Right. Because some galaxies, if they're far enough away, can appear as point sources. Yes. Yes. And it can also appear very red, right? Yes. Yes. So we knew this was a problem, and you can look across this. There's like little tiny other point sources on there, and you say, Susan, maybe those planets too. Yeah, this one, that one. You might be right. Some of them might be planets. But the reason we didn't like shout those from a mountaintop is because you have to search too much area of the sky. They're not close enough to the white dwarf to be able to say, well, statistically speaking, like what are the odds that you would find a smudge within a big area of sky given the rate at which you see background galaxies, right? Yes. Yeah. Right. But when you find it so close to the white dwarf, you say, well, what's the odds it would be that close, right?
And so these were the statistics we went through. We counted up all the red point source things in our images for both, or actually for all 4 white dwarfs, to figure out what the rate of finding these kind of background galaxies are.
Perfect.
And said, what are the odds we would find one so close to our white dwarf if it was a background galaxy? And if you do that, the odds are extremely low for both stars, better than 2 sigma.
Okay, good.
That's why he published this. And then the odds of both of them being false positives is extremely low, because now you've searched all 4 stars and you found 2 amongst 4 stars. You start asking really hard questions. It's something like 1 in 3,000 if you think of it that way.
Okay, right. Very cool.
So
thanks for sharing the total image. I think this is important to see, right? I mean,
this
all
is
of figure 1 is right here, right?
That's right. That's all
65 pixels across there.
That's right. And so you see like all the potential that is actually in these images, because there's, this is just an image of the sky. So if someone wants to go off and use this data later to study the galaxies that are in there, please have at it, right? I've gotten what I need out of this data, and there's potential to do more, I'm sure. Stars, right?
Very cool.
Yeah.
Okay. Well, thanks for sharing that. That was very good. Let's go back to the article. I think we have one more figure to go.
Yes, we have one more figure to go, just to kind of say why also these planets are really cool, if you'll accept that pun, because they are quite cool.
They're red. They're red.
So what's really neat is that if we can confirm these are planets, and we can talk about that too, that these planets would then expect to be the same age as the star they're orbiting, right? They expected them to form at the same time as their star, so which we know reasonably accurately with because we have a pretty good sense of the age of the white dwarfs. So, well, I mean, some better than others, but we do know they're in this, you can see the error bars there. We know that they're billions of years old, which means that we are able to find planets that are billions of years old. It means the planets are extremely cool. We're talking about things that are a couple hundred Kelvin. Whereas most planets, which are the black points on here that have been found so far, are actually around very young stars. Notice that y-axis is a log scale.
Yes.
The only way to get it all on there. There are very few points I can put on this plot that are older than 1 billion years old. We have our solar system, and then I put that Y brown dwarf binary that was found as well. But then there would be these planets that are billion-year-old planets. So JWST is opening up the opportunity to study billion-year-old solar system age planets around other stars.
Very cool. Because we will be there one day.
We are there. That's the thing. We are billion-year-old planets already.
We don't have a white dwarf yet.
We're just not the white dwarf stage. That is how we're still not similar to the solar system. Oh, one other point that might be worth making is that those planets, right now they're at about, you can see compared to the solar system there, which are those blue stars. But one of them is about a Saturn distance, and the other is out at like Neptune.
Yes. Okay.
If you rewind time and assume that an adiabatic expansion happened as the star lost its mass, the planet would have moved outwards. So if you rewind time and bring the planets back in during their main sequence days, those planets actually were at distances that were more like Jupiter and Saturn during a main sequence time is what we would expect them to be.
Well, this is great.
In many ways, these planets are very similar to planets in our own solar system, and we're kind of seeing what our solar system might look like after our star dies. Yeah,
that's actually pretty cool. You're getting a sense of the migration outward.
Yeah, exactly. What we have. And so there we go. So what's left to do, I think, is this is our evidence that we have them. They're really neat planets because they help us connect that metal pollution on the surface of the white dwarf. So we have more concrete evidence that is what's driving all that metal pollution we see on the white dwarfs. And it's showing that JWST is able to image billion-year-old giant planets around other stars.
Very cool. That is so awesome. That is awesome. Susan, thank you so much for walking us through this discovery article. Very nice. Let's see, and you touched on it a couple of times, or you opened up threads, I should say. So let me ask, where do you think we go from here, given the published article? For one, you're calling them candidates. How do we remove the candidate label onto? Yeah. For sure. Are there other systems? Are there plans to go after, let's say, make the sample size here 10 times bigger? Are there other wavelengths that could be done? Things along these lines. So where do you think we go next steps?
So the immediate next step is, yes, let's confirm these. We just found out last week, actually, that JWST TAC has decided, yes, we get to confirm these.
Oh, cool.
The best way to confirm them, I mean, there's more than one, but the easiest way is to just look for common proper motion. These white dwarfs are so close, they have such high proper motion, they're like 200 to 400 milliarc seconds per year. They're booking it across the sky.
Yeah.
So in a couple years, they'll move like by many pixels on the sky.
And that smudge should stay with it.
The smudge should stay with it. That's right. So if they move together, then we know we have a planet. And if they move past it, then we know we do not. So we will get those observations probably early next year, if I had to guess, just when the observing window was. But we'll see how it gets scheduled. And so yeah, JWST will hopefully let us do that, and so we'll be shouting that from the mountaintops either way to let you know what happened. But yeah, like this opens up a lot of possibilities for how we can go about finding planets that are similar to those in our own solar system, and white dwarfs actually open up this cool possibility that the planets really are there, right? We now know they're there. So we could do a survey of nearby white dwarf stars to look for planets around them. But I will, yeah, easy peasy, right? All I have to do is take a bunch of images. I will point out that our 15 micron images, which look really deep, actually have exposure times of about 2 to 3 hours. So this is not, so each star is, these four stars took us 25 hours to observe total.
Right.
So if you want to do a sample of 20 or 50 white dwarfs, right? So you could find all the nearby planets around white dwarfs. It starts to look like hundreds of hours of JWST.
Right.
But if you want to find a sample of Jupiter mass, billion-year-old planets, this is a way JWST could go out doing that. And if we do that, then we could follow them up with JWST to get spectra. We can compare them to the atmospheres of planets in our own solar system. We can better constrain those models then, right? And get a sense of whether our Jupiters and Saturns are actually representative or not of other exoplanets.
Ooh, that's an interesting question. Right. Definitely.
Right. Definitely. So, and we'll know more about what actually really happens after planets evolve off, or after planet stars leave the main sequence stage. Additionally, if we continue to follow these two planets we found, we actually could map out their orbits. They're close enough that they will swing through, assuming they're circular, whatever, they swing through maybe 30% of their orbit in the lifetime of JWST. So we could actually see if they're eccentric orbits, how, and do those kind of mappings as well. So we could learn more about those as well.
Very cool.
So there's lots of possibilities. And I look forward to trying to pursue them.
Very cool.
But I have to admit, we're doing the science with a very oversubscribed telescope. So we're gonna have to make some convincing cases.
Indeed. But it's really exciting. It's very, very exciting.
Thank you.
So congratulations. Beautiful work. And I really look forward to seeing it develop over at least JWST lifetime, if not just a couple of years. So
yeah, we should know more by next year this time. So I'll let you know.
Awesome. Thank you. And that will do, everyone. And I hope this made your White Dwarf Astronomy Day just a little bit better. And see you on the next one. Bye-bye.
Bye.